So now we're going to look at how we would actually use the Schwarzschild metric in problem 23. How close to the center of the sun can you approach before your spaceship's clock differs from time measured in flat space-time by no more than, in part A, 1 second per year? Is this larger or smaller than Earth's orbital radius? So we're going to need information from the appendix, which I don't think I have with me, but you can look up the mass of the sun in the appendix, and the mass of the sun is 1.993 times 10 to the 30th kilograms. So we're talking about the sun, so we're using the mass of the sun. Remember, that's at the origin of our coordinate system. And in part A, we want to look at when the difference is no more than 1 second per year. So we have our metric here. And just like when we did the Minkowski metric, we often just use dx and we ignored dy and dz because we were just moving in one dimension. Similarly here, there's no motion in the tangential direction, so we're going to say ds squared is equal to 1 minus 2 gm divided by c squared r times c dt squared minus dr squared divided by 1 minus 2 gm divided by c squared r, and that's it. Okay, now, is the spaceship actually moving? We are going to assume the ship is at rest. So it's just hanging out at some different distance from the sun, and we want to compare clocks on the spaceship to clocks that are very far away back in flat space-time. So remember that T is the flat space-time, the time measured on clocks very far from the central mass where space-time is assumed to be flat. So this dt is for flat space-time, and dr is equal to 0 because we're going to assume the ship isn't going anywhere. So we know g, capital G is a constant. We know the mass of the sun. We know c squared. We are looking for how close you can approach. So we're trying to find r. But we don't really know dtf. But we do know how time in flat space should compare to time on the spaceship. So first of all, we want to know who is going to measure the longer amount of time. So time slows down as you approach the large massive object, so we can say dt on the ship divided by dt for the people in flat space should be, the difference should be no more than 1 second per year, and the people who measure the longer time are going to be the people who are farther away. So 1 year on the ship should be no more than 1 year plus 1 second for the people far away. So now I have one equation here, which has the r, which I'm trying to find, and the dtf, and I have this relationship here. But I also know that this interval ds squared should be the same for everybody. So I used it here with a time for flat space because t is the flat space time. So now I have to find another equation which uses the time on the spaceship to find ds squared. Now here's the thing that gets a little tricky. So even though this is the metric that we use when mass distorts space-time, the time that we use here is for the people who are really far away from the object which is in the gravitational field. For the people on the spaceship, you can say that they don't really know that space-time is distorted where they are. So if you're really far away, let me go back to the diagram that we had for the Schwarzschild metric. So if you're really far away, you can tell that here space-time is distorted. But if you were close, like if you were right here, space-time would look flat to you. So the people who are in the spaceship actually get to use the Minkowski metric. So for the spaceship, we have ds squared is equal to c dt, but this is for the spaceship, squared, minus what would be dx squared, but we're assuming that the ship is at rest. So dr squared is equal to 0, and dx squared for the people in the spaceship is equal to 0. So this would just be minus 0. So we can set these two equal to each other because ds squared is the same for everybody. So now I have c dts squared is equal to 1 minus 2gm over c squared r. Remember, I'm trying to find r, times c dtf squared. I want to find this ratio, so I'm going to divide both sides by c dtf squared, then I'm going to take the square roots of both sides, and even before I do that, I can say the c squared here is going to cancel with the c squared there. So if I divide by dtf squared and then take the square root of both sides, I have dts divided by dtf is equal to the square root of 1 minus 2 gm over c squared r. Now what I want to do is put in the numbers for part A. So this is 1 year over 1 year plus 1 second, and I know the units don't match, but I'm going to worry about that later. And this is the square root of 1 minus 2 times g, which is a constant, and I think that is in the appendix also. So let me find my appendix. Okay, so if you look on page 1 of the appendix, we have the constant capital G is 6.674 times 10 to the negative 11th newtons times meters squared per kilogram squared. I think we'll try and squish the units in here. Okay, so this is newtons times meters squared per kilogram squared, and this is times the mass of the sun, which is 1.993 times 10 to the 30th kilograms, just like we said up here. And I divide all of that by c squared, so that's 2.998 times 10 to the 8 meters per second squared times r, and we're going to solve this for r. Now, we're going to do 2 times this divided by this, so that will be something divided by r. That should have units of meters, so let's just make sure that the units work out. So this is kilograms squared, and this is kilograms, so one of those cancels out. And then I have meters squared here, and meters being squared there, so that cancels out. And a newton is a kilogram times a meter per second squared, so I've got the kilograms here. I want the meter, and the second squared cancels out, so the answer is going to be in meters. So this is square root of 1 minus, this is 2,959.8. Let's just round that to 2,960. So this is 2,960 meters divided by r is equal to 1 year over 1 year plus 1 second. So now we get to do a little bit of algebra to solve for r. So we're going to square both sides, and then I move this over to this side, and then 1 year divided by 1 year plus 1 second over to the other side. So I get 2,960 meters divided by r is equal to 1 minus 1 year over 1 year plus 1 second squared. Then I have to take the reciprocal of each side, and then I can multiply by 2,960. So that gives me R is equal to 2,960 divided by 1 minus 1 year plus, divided by 1 year plus 1 second squared. So we have to convert the years to seconds. I don't want to write this all out, but it would be however many days are in a year. So let's say 365.25 times 24 hours per day times 3,600 seconds per hour, which gives us something like 31.56 times 10 to the 6th seconds per year. So that would be in the numerator, and then in the denominator it would be the same number plus 1, and that should be something like 0.999999968. So it would be 1 minus that squared, and then do 2,960 divided by that, and that should give us R is equal to 4.625 times 10 to the 9th meters. At least your first two significant figures should be the same. And if you get something that rounds to 4.7 instead, oops, this is times 10 to the 10th. If you get something that rounds to 4.7 instead of 4.6, that would be fine also. So actually, I think it would be better just to say 4.6 times 10 to the 10th meters. So that is the answer for part A. Then for part B, what if the difference is 1 second per week? Now the only thing that would change in our formula is what we have here. So for part B, it would be R is equal to 2,960 divided by 1 minus 1 week over 1 week plus 1 second squared. So you could take 3,600 seconds per day times 7 days in the numerator, and then in the denominator it would be the same thing plus 1, and for that we should get 8.95 times 10 to the 8th meters, and I forgot when I was telling you this to do times 24 for 24 hours per day. So that gives us this. And is this larger or smaller than the sun's radius? Oh, and then for part A, we are supposed to answer, is this larger or smaller than Earth's orbital radius? So for Earth's orbital radius, you can look at the Earth-Sun distance from the appendix. This is 1.46 times 10 to the 11th. So that would be smaller than the orbital radius. And this we're comparing to the sun's radius. So the radius of the sun is 6.93 times 10 to the 8th. So is this larger or smaller than the sun's radius? This would be larger than the sun's radius, but not by that much. I think actually we should check the answer in the back of the book for this. So this was 8. So they say 8.93 times 10 to the 6th there, but I'm pretty sure that this is a mistake, and this is supposed to be times 10 to the 8th. So as long as that is a mistake, this would really be larger than the radius of the sun. And then for part C, at what rate would your clock run slow on the surface of the sun. So now we're not looking for r. Now we already know r, and we want to figure out what dTs over dTf is. So for part C, I have dTs over dTf is equal to 1 minus 2 times g, which is 6.674 times 10 to the negative 11th, times m, which is 1.993 times 10 to the 30th, divided by c squared, which is 2.998 times 10 to the 8th, times r. Now, if you're on the surface of the sun, you would use the sun's radius for r, so this is 6.963 times 10 to the 8th. Whoops, I didn't put units in for anything else, but the units should all cancel out, so this should just be a number. And let's see what that gives us. Okay, so this times this times this divided by this is 2,960. I did kind of round that, so it's 2,959.78551 if you want to use a more exact number, divided by 6.93 times 10 to the 8th, which gives me the square root of 1 minus 4.251 times 10 to the negative 9th. 251 times 10 to the negative 9th. Okay, now we don't actually want to know this fraction. It says the rate at which they run slow. So what we're going to do here is use the approximation. Since this number is really small, this is approximately equal to 1 minus half of this. So half of that is 2.125 times 10 to the negative 9th. And then the rate at which they run slow would just be the 2.125 times, oops, is it times 10 to the negative 9th? No, because this was actually supposed to be to the negative 6th. And this is also then times 10 to the negative 6th. So this is the rate at which they run slow, and that concludes problem 23.